Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good morning, everyone. We're very happy to have Raghu Meka from the IAS, who will tell us how to beat the union bound.
So I'll talk about beating the union bound by geometric techniques. So what is the union bound? It's a basic fact in probability theory. It says that if you have n events over some probability space, then the probability of the union of the events is at most the sum of the individual probabilities. In particular, if the sum of the individual probabilities is less than 1, then with non-zero probability, none of the events occur. And this was popularized by Erdős, and it's one of the most basic techniques in the probabilistic method. But even before Erdős, there was one literary figure who made prominent use of this, and I'll give you 3 guesses. Literary figure. Okay, close, but
what was the question?
There's one literary figure who made use of the union bound before.
I could say Sherlock Holmes.
Exactly. He said that when you have eliminated the impossible, whatever remains, however improbable, must be the truth. It's kind of a paraphrasing of the union bound. Okay. So despite its simplicity, it's amazingly effective in the probabilistic method. And some notable examples are the original application of the method by Erdős to showing the existence of Ramsey graphs, very good Ramsey graphs. And Shannon, who also used it to show the existence of very good error correcting codes. Johnson Lindenstrass, who used it to show the existence of very good metric embeddings, and so on. There are many other such applications, as can be seen in this beautiful book by Alon and Spencer. On the other hand, sometimes the union bound is indeed too naive, and it's not enough to capture the full picture. And one salient example of this is the Lovasz local lemma, which says that if you have n events as before, but the events are d-dependent, meaning each event depends on at most d other events, and the probability of each event is not too large, then the probability of the union is at most 1, is less than 1. And if you use the union bound here, you get nothing if n is much larger than the degree d. So it beats the union bound. And we'll keep seeing this symbol whenever we succeed in beating the union bound. And this result itself, this existential result, is amazingly effective. And as Spencer says, it helps us find needles in haystacks. On the other hand, we'll come across this concept again, which is to make this result constructive or algorithmic. And this required further breakthroughs by starting with the work of Beck, and more recently with the work of Moser and Tardush, and so on.
It should be indeed this formulation, not false.
Oh, right. I guess this is the first Lovasz and Erdős formulation. Yeah, yeah. 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 I think in 77 it was 4 and was improved to E later on. This is the first result had a 4 in it. So here I'll talk about 2 examples. The first about beating the union bound. The first is to constructive discrepancy minimization. And here I'll talk about a new approach for rounding linear programs by Brownian motion. And then I'll talk about a limit theorem for polytopes. And here I'll just state the result and give some applications to learning theory. And in both cases, we will use some nice symmetry and geometric properties of the Gaussian distribution to go past the union bound. And that kind of serves as the underlying or unifying theme between these results. And here's the outline. I'll talk about the 2 parts. And then finally, I'll finish by mentioning some of my other results and summarizing the work. So let's start with the first part. So in the basic setting here in discrepancy minimization is you have a set system, which is a collection of m sets over some universe of size n. For example, here, let's say the universe is of size 5, and S1 is the set 1, 3, 4, S2 is 2, 3, 5, S3 is everything, and so on. Okay. So a collection of sets like this, and the goal in discrepancy minimization is to color the elements red or blue so as to minimize the maximum imbalance. So for example, let's say we consider this coloring here. Then the first row has an imbalance of 3. The second row, or the second set, has an imbalance of -1, and so on. So the maximum imbalance or the discrepancy of the coloring is 3. And the goal in discrepancy minimization is you're given a set system, and you want to find a coloring chi such that which minimizes the maximum over all sets in your set system of the discrepancy. And this is a fundamental combinatorial concept with many applications. And let's look at a few examples to familiarize ourselves with it. And one of the first and notable examples of bounds in discrepancy was a celebrated result of Roth from '64. We showed that if the sets in your set system correspond to arithmetic progressions over Zn, then the discrepancy is at least n to the 1/4.
Is m equal to n?
Here?
Yeah.
Here m can be much larger. It's usually about n squared.
Oh, is this uniform over m? Wait, how does m come? All.
So m is set of all. M is the size of the set
Yeah.
system, and here you are taking all arithmetic progressions. So there'll be roughly about n squared sets.
Okay.
Like you have the set 1, 3, 5, 7. You also get 2, 4, 6, and so on. And Matuszek and Spencer also gave a matching upper bound. And another example that is well studied is the case of half spaces. So here you have a bunch of points over some, let's say, the plane, and the sets in your set system correspond to indicator functions of half spaces. So you draw a hyperplane, and all the points on one side will correspond to one set, like S1 here. You draw another hyperplane, and all the points in this side will correspond to S2. And you consider all possible hyperplanes and all possible sets that you get in this form. And once again, we have tight upper and lower bounds for the discrepancy of this set system as well. Okay. So discrepancy minimization and discrepancy theory has many applications, and here I'll talk about one cute application that I like to ray tracing in computer graphics. So ray tracing is a very kind of a nice concept in graphics where you give some textual description of some figure. There's a sphere at so and so coordinates, there's a slab at so and so coordinates, there's a triangle somewhere, and so on. And the goal of the ray tracer is to take this text description and render an image that corresponds to this description. Okay? And this image is actually generated by one such ray tracer, which I was glad to use because this is from an undergrad project I did long time back. Okay. So how does the ray tracer work? So ray tracer works as follows. You specify the position of the camera and the position of the screen, and there are objects that you're trying to render. So it shoots some rays from the camera, finds out where the rays intersect the objects, and then retraces back onto the screen, and then renders them according to the properties of the intersection point. It's a very simple concept, and one important operational question here is to decide which points to shoot rays from. For instance, we can't shoot the rays from all the points on the screen because that would be too computationally intensive, and the choice of the points makes a big difference in the quality of the rendered image. For example, if you choose the naive grid, then you get a lot of aliasing errors. And what people do in practice or in graphics is to choose a set of points whose discrepancy with respect to simple geometric shapes like half spaces, triangles, circles is small. And this is like actually what practitioners use. They compute some, they have some preset configurations which minimizes discrepancy, and they use this in their ray tracing programs. Okay? And more generally, discrepancy has many applications. I think the intuition is that when you do this, every shape gets kind of the same number of points, but the evidence is probably more empirical. You can really clearly, I mean, if you do it, if you run the program, you can clearly see aliasing errors being minimized with respect to discrepancy. So it's probably more empirical.
Somehow I'm missing something. I mean, wouldn't a grid be almost as good as anything?
No, the grid is not so good. Why? Let's see, because it depends on how fine a grid you choose. So if you fix the number of points, then the grid is not as good as some other configurations.
Why?
So for instance, if I take let's say I take a square, which is smaller than the resolution of the grid, then you're kind of, or like a rectangle which sits inside between the two lines.
There are sets that do much better than that.
So you can do well with grid too, but then you would require finer and finer resolution or more points.
But I mean, for a small square, the grid's more or less as good as anything up to some point.
Yeah. For the thing is, how small a grid do you need?
Yeah, but for a given set of points.
For a given number of points,
Given number of
configuration
points.
is much better than the grid.
For small squares, I mean, it's a question of which collection of sets you're trying to.
Right. So let's say you take a rectangle,
Okay, very, very
thin rectangle.
Then
You don't want to lose those two. Right? Shapes like that might be problematic if you use the grid. And discrepancy theory has many applications in complexity theory, where they correspond to good average case lower bounds, to communication complexity, where it is one of the main techniques for proving lower bounds, to computational geometry, where it is useful in building small data structures, and to graphics, as we saw before, and also to pseudo-randomness. And there are many more applications, as can be seen in these two nice books. And here I'll talk about one of the cornerstone results in this area, which is this Spencer's celebrated 6 standard deviation suffice theorem. It says the following: if you have a set system with n sets in it, then the system has discrepancy at most 6 times square root n. And it's called the 6 standard deviation suffice result because there's a 6 in the theorem statement, and square root n corresponds to the standard deviation of a set under random coloring. And the square root n bound here is actually necessary. We don't know the right constant in front of it, but more or less it's tight. And what's most interesting here is that it beats the union bound. If you take a random coloring and use a union bound across the different sets, you can show that the coloring gets discrepancy square root of n log n. But on the other hand, there exist set systems where random colorings get you discrepancy theta of square root n log n. So Spencer's result beats the union bound in this sense. Yeah? Oh, I forgot. And another aspect of this result is that Spencer's original proof had an ingenious use of the pigeonhole principle and hence was non-constructive. So it gave no algorithm for finding such a coloring short of enumerating all possible colorings. And in fact, Allen and Spencer conjectured nearly 20 years ago that there is no efficient algorithm for finding such a coloring which gets discrepancy O of square root n. And like all good conjectures, this was shown to be false. Recently, in a breakthrough work by Bunsell, we showed that there exists a randomized algorithm for finding a coloring with discrepancy O of square root n. And here, I want to talk about a new elementary and geometric proof of Spencer's result, which also gives an algorithm to find such a coloring. And I want to stress that our result is truly constructive in the sense that even though Bunsell gave an algorithm for the problem, the analysis of his algorithm still appealed to the non-constructive proof. So he had some semi-definite programming relaxation, and to argue about the value of the program, he used Spencer's non-constructive proof, whereas our algorithm itself gives a proof of the result. And more than the specific result, I think the technique we introduced for finding such a coloring that we call Edgewalk, which involves some rounding linear programs by Brownian motion, seems to be of much broader potential and could be used elsewhere. And very recently, about 2-3 weeks back, Lovasz used some of our techniques to give the first improvements for the bin packing problem in nearly 30 years. So it seems to have other applications which merit further investigation.
Can I ask a question about the randomized algorithm? When you say in this context, does that mean just with a fixed probability, your algorithm will give you what you want?
Right. And you can also make it deterministic, but I think here the punchline is just finding one such algorithm. And here's the outline of the algorithm. I'll describe the algorithm in its full glory and also sketch its analysis. So the algorithm involves 2 steps. One is the partial coloring method, which was used by Spencer and we will also use. And next I'll describe the Edgewalk algorithm. So let me start with the partial coloring method. So the partial coloring method was introduced by Beck, and the philosophy is as follows. In the discrepancy minimization problem, we said we want to find a red, blue, or 1 minus 1 coloring. And Beck suggested instead let's find a 1 minus 1 0 coloring, so where some of the variables might get a value of 0. But if you don't put any restriction here, the problem becomes trivial. You just output the all zeros vector. So Beck suggested instead let's find a partial coloring where at least half of the coordinates are non-zero. And the idea is as follows. Let's say you find a partial coloring where half of the coordinates are non-zero, like the one shown here. And he suggested once you find such a coloring, let's hide the things which are non-zero. Let's forget about that and recursively solve the problem on the remaining unfixed variables. So you find another partial coloring on these guys, maybe n over 4 elements, and then repeat the process until you cover the whole all the set of variables, all the variables. Okay, and if everything works out according to plan, the hope is that the first partial coloring gives you a discrepancy of square root n, and the second partial coloring gives you a discrepancy of square root of n over 2, because now we are working over a universe of size n over 2, and then n over 4, and so on. So you get a geometrically decreasing series, and the total discrepancy is O of square root n, which is what we want. And more concretely, the first step is you have a collection of n set systems, n sets over some universe of size n, and you want to find a 1, 0, minus 1 coloring such that the coloring has small discrepancy, O of root n, and most importantly, at least half of the coordinates are non-zero.
And it's really n is the number set and the size.
Right, so here I'm simplifying. If you put an m there, it will be square root of n times log of m over n. But I think this is the main step. Once you get this, it's not too hard to get to other things.
So it's square root of what? Number of sets or number of elements?
Oh, here it's square root of number of variables, number of elements, times log of m over n. That's the precise bound. And our main result is that there is an efficient algorithm to find such a coloring. And that's what I'll talk about. And because there is an efficient algorithm to find such a coloring, as a corollary, we get that there exists one such coloring, which was the main point of the previous results. Okay. So let me now talk about the Edgewalk algorithm. And to motivate the algorithm, let me rephrase the problem in a geometric language. So here's the discrepancy setup. You want a coloring which minimizes the maximum imbalance. But there's a different way, or perhaps more intuitive way of measuring the discrepancy, which is to look at the matrix vector product of the incidence matrix of the set system with the coloring vector. Then the discrepancy of the coloring is just the maximum entry in absolute value of the matrix vector product. So you want a plus or minus 1 vector so that the infinity norm of the matrix vector product is not too large. And further, if we let v1 through vm be the indicator vectors of the sets in your set system, what we want is a coloring chi such that the inner product of chi with each of the indicator vectors is small. And now these constraints, the inner product of chi with the indicator vectors being small, these are all linear constraints, except with the caveat that you want chi to be a plus or minus 1 vector. And this naturally suggests the approach of looking at the linear programming relaxation for the problem. And if you do that, you end up with the following polytope. P, which is a set of all x, so that each entry of x is at most 1 in absolute value, and the inner product of x with each of the indicator vectors is small. So this is the linear programming relaxation of the discrepancy minimization problem. And our goal is to find a non-zero lattice point inside this polytope. Not just a non-zero point, but an integral point which has many non-zero coordinates that would correspond to a good partial coloring. And in the rest of the talk, I'll refer to the constraints of the form absolute value of xi at most 1 as color constraints, because that's where they come from. And the inner product constraints as discrepancy constraints, because they correspond to the discrepancy of the set system. So here's the setup again. You have this polytope, and we'd like to find a highly non-zero lattice point inside this polytope. And for intuition, let's use the distance from the origin as a proxy for how non-zero a point is. That's just for intuition. And so we are starting at the origin, let's say. And our goal is to find a vertex which is kind of as far away from the origin as possible, but still inside the polytope. And the way we do this is to use Brownian motion. So we do a random walk in n dimensions until you hit the boundary of the polytope. And once you hit the boundary of the polytope, we need to decide what to do. We still want to keep moving away from the origin because we want to increase the distance from the origin. On the other hand, we don't want to cross the polytope. So we take the greedy approach, which is to do the Brownian motion, but now constrain yourselves to lie within the boundary that you hit. So you do a random walk or Brownian motion until you hit another constraint, and then you repeat the process until, lo and behold, you hit the vertex that you wanted to get to at the beginning. So this is the full algorithm. And the claim is that this algorithm will find a good partial coloring. Okay.
So this Brownian motion is through fractional points.
Right. So if Brownian, yeah, it is through fractional points. Yeah.
And what is your stopping criteria?
So in morally, the stopping criteria is just go until you reach a vertex.
Vertex of the polytope.
Vertex of the polytope. But in reality, we'll just stop after a certain number of iterations because we want it to be a discrete walk.
But this final point is also likely to be fractional?
So most of the coordinates will be integral, except some coordinates. Half the coordinates will be integral, half the coordinates will be fractional, and will then recurse on the fractional coordinates as before. So half the coordinates will be integral. That's what we want to show.
You can hit either
the phase, sort of coloring phase, or
the discrepancy discrepancy. Exactly, that's the point. So, I mean, let me describe the algorithm fully, because this continuous Brownian motion is not exactly is nice for intuition, but when you try to implement it, it's a bit problematic. So, to make the algorithm formal, let me describe what's the random walk that we'll use. So the random walk is pretty natural. You have some subspace V, and given your current position, you just choose a random Gaussian vector in your subspace and take a step of length size gamma in that direction, where gamma is some step size. You want to take tiny steps, not too large. So the walk looks something like this. Okay? And another minor issue is that in the description, I said you stop the walk once you hit a face. But if you're doing a discrete walk, you might not hit the face, but might overshoot it. And the solution is just to introduce a slack near each boundary. So if you get too close to the boundary, then we'll say we hit it. So let me now describe the algorithm. So the algorithm gets us input some vectors, which you should think of as the indicator vectors of your set system. And it runs for a certain number of steps, which depends on the step size gamma, but let's not worry about the parameterization too much. So you start from the origin, and at the tth step, let color t denote the set for all color constraints or color faces that are nearly hit. This is the set of all coordinates I, such that the absolute value of the ith coordinate is very close to 1. And let discrepancy t denote the set of all discrepancy constraints that are nearly hit. This is a set of all vectors vj, such that the inner product of vj with our current vector is very close to the threshold that we don't want to cross. And as I said, you still want to do the random walk, but not change any of these constraints which are very close to being violated. So we just walk in the subspace that is orthogonal to all of these constraints. So if you let Vt be the subspace, you just pick a random Gaussian vector in that subspace, take a tiny step in that direction, and repeat this process. And the number of steps you have to do this will roughly be 1 over gamma squared, where gamma is the step size. So that's the algorithm. And the claim is that this will find a good partial coloring with some non-negligible probability. Now let me give the sketch of the analysis, and the actual proof is not too much more complicated. You just have to write some tail bounds, but it's not too hard.
So just to make sure I understand, you may overshoot slightly or whatever.
So it happens with very tiny.
Land on the face, but then you stay at the point you're actually at. Nevertheless, you don't actually round it to the face.
So it happens with so little tiny probability that you kind of ignore such events. So if your step size is much smaller than the slack you introduce, you're never going to overshoot the poly.
But you stay actually off the face by a little bit.
Yeah.
You don't round it onto the top.
So you can think of the slack as being polynomially small, such that at the end, if it's 1 over n, you can just round it to anything you want. It's not going to affect the error in the discrepancy problem.
Could you use Brownian motion if you didn't care about the computational efficiency?
I think so. Yeah, probably. But this, yeah, you should be able to. Brownian motion is basically like the case where gamma is going to 0. So now let me describe the analysis. The setup is the same. You have this polytope, and we'd like to find a highly non-zero lattice point. And the punchline for the analysis is that the discrepancy faces are much farther from the origin than the color faces. Okay? So let's say we're shooting for a constant of 100 times root n. Okay? Then the discrepancy faces are at a distance of 100 from the origin, because each of these vectors Vj has norm at most root n. And the color faces are at a distance of 1 from the origin, because they're just of the form xi is less than or equal to 1. And by design, by the way we design the random walk, it looks Gaussian in any direction. with some variance. So you do some calculation of some martingale tail bounds, and you get that the probability that the walk hits a discrepancy phase is roughly exponential in minus 100 squares, like a sub-Gaussian tail. And the probability that the walk hits a color phase is roughly exponential in minus 1. It's not too small. Okay? And as a consequence of these two bounds, you get that the probability that the walk hits a discrepancy phase is much smaller than the probability that it hits a color phase.
You mean the probability it ever hits one?
It's
On the first?
so you fix any discrepancy phase and any color phase, it's more likely to hit the color phase. And then when you take a kind of expectation or all the discrepancy phases.
But again, the question is, when you say walk hits, do you mean the probability that it ever hits it? This entire process that you've defined with the faces and so on.
Right.
That's what you mean.
Yeah. Okay. And because of this comparison, what's morally true is that you end up hitting the cube faces more often. Okay. And let's say you don't worry about those discretization issues and you run the walk until you reach a vertex. But when you reach a vertex, you should have hit n constraints. And we know that most of them are color constraints. And if you're satisfying n constraints and most of them are color constraints, half of them must be color constraints. That means you get a good partial coloring. Okay.
Just to clarify, so the estimate you have there on the top is you're talking about one round from the origin until you hit some constraint, right? When you say the probability you hit the discrepancy phase is smaller. Color phase.
So this is over the entire run of the algorithm. Let's fix a discrepancy phase. The probability that hits that discrepancy phase is much smaller than the probability that hits any of the, or an average cube constraint.
So this norm reason you gave, it's clear the first time it hits, it's not clear.
Right. But the same kind of intuition actually works even afterwards. Because, I cheated a little bit, and you're catching me on that, is that it's not any color phase, but like most of the color phases. So it might not be true for, let's say, x1, but it'll be true for majority of the color phases.
We just have to understand the quantifiers here. You are fixing two phases, one discrepancy phase and one follow phase, and
right.
Saying what's the probability that it hits
the discrepancy phase throughout the run of the algorithm. It's roughly this guy.
I mean, if this was true, then with high probability you would never hit any discrepancy phase in the entire.
No, but there are many of them, right?
Yeah, but they're not exponential.
100 is a constant.
Squared times as many.
100 is a constant here. You should think of maybe if you put a 6 here, then it might make sense. It's a constant, and the number of discrepancy constraints might be larger or is comparable to the number of color constraints.
But really, this when you say a half, you could improve that to exponential.
Yeah. Right.
Yeah. But once you hit one of those discrepancy phases, so your random walk is no longer
truly Gaussian. But what happens is the first inequality still holds, because if you look at the projection, it's a Gaussian with lesser variance. So you're doing better. And for the other guys, it won't be true for every color constraint, but it'll be true on average. And it's like the intuition, and you write down the calculations, it'll come out to be true on average. You might decrease the variance for one of the color constraints, but not for all the directions simultaneously. Okay? So that's basically the proof, and you just have to write some tail bounds and use this averaging argument to formally verify it. And the key point here is that we use the symmetry of the Gaussian distribution to argue this fact, and that's where we end up beating the union bound in the analysis. Okay? So let me summarize. So you use our Edgewalk. We call it the Edgewalk algorithm because you're basically trying to walk on the edges of the polytope as much as you can. And so it gives an algorithmic form of the partial coloring lemma. You find a good partial coloring. And then you recurse on the unfixed variables as in Spencer's original argument. And you combine these two to get Spencer's theorem. So here's the symbol now.
When you optimize your bound, what constant do you get?
So I wasn't completely sure. I did some crude estimates and wrote some MATLAB code to figure out the constant. It came out to be 13, which probably can tweak it better, but some first order approximations say 13.
So, sorry, just to make sure I understand, when you choose the amount of this slack for the faces, you're saying you can do that in a way that just depends on n.
On n.
Doesn't seem obvious to me because I mean somehow it might depend on like how close the edges get to each other or something. But I guess it's
So
the
so
magic of the Gaussians and so on.
right. So you choose it. Let's say you choose it 1 over n squared or something, okay? And you'd run this whole algorithm, and then you whatever slack you have, you just round it to the nearest 1 or minus 1. And because it's 1 over n squared and each vector has norm n, you don't hurt yourself much. So before moving on to the second part, let me just say that the algorithm I described, you can do it for any polytope. This is just a random walk on polytope. So you just start from the origin if it contains the origin, or start from any point inside the polytope, and then repeat the process as before. And here, let's look at kind of the ideal scenario where you do the Brownian motion. And it seems to introduce some strange distribution on the vertices of this polytope, which kind of is skewed towards vertices which are closer to the origin in terms of the bounding hyperplanes.
So,
Yeah.
rounding is.
It's like an iterative rounding.
You're misusing the term rounding here.
It's kind of an iterative rounding scheme.
Well, it is rounding, right? You take a fraction point and return a vertex.
It's really, you're returning a vertex of the polytope. Anyway, in rounding, you start with the vertex of the polytope.
No.
Well,
You
depends
can
on
do a fraction
you
of
want to
point.
start
Start with a fraction.
And you just up on one of the here, right?
No, in rounding, you optimize a linear function, you get a vertex of the
Okay,
polytope.
that's a special case of rounding. Rounding is.
No, but depends on the two polytopes, right? One is the relaxation polytope and one is the your integral polytope.
Right.
You could have made the same complaint to me yesterday, but you didn't.
So should I think of this as the integral polytope?
Yeah, it's like you're trying to find an integral solution. So you find this fractionally integral solution, and then you iterate on the remaining things and so on.
The problem is if I have let's say I have the integral polytope, the convex sum of all the integral points, then I don't know what the hyperplanes are. So I can't really do it.
Say it again.
So if I have, let's say I start with the integral polytope, which is the convex sum of all the integral points I want to optimize over,
Right.
then I don't know what the hyperplanes are.
Right.
Then how do I do this?
You might know, like it might be the spanning tree polytope, then you know.
Well, if my polytope is integral anyway, then yeah, I mean, I would already there's no rounding needed.
Or for any polytope, you just so here's the rounding algorithm. If you want, you have a fractional solution. You do this walk, and you get some vertex, and you look at the coordinates of the vertices, which are now integral.
But none of them will be integral, right?
If it's not, then the rounding algorithm has failed. But that's the approach. So you find some coordinates which are integral, okay?
Maybe none of the word.
Yeah, then the algorithm is failing for those kinds of. It's not a universal rounding algorithm. Right? So if it succeeds, it will succeed. So this is the approach for finding an integral solution.
So, I mean, so it will work if these vertices of the polytope are such that they have many integral coordinates.
But that's the success. I mean, that's when it
What I'm
succeeds.
saying is, if the polytope is guaranteed, has this property to begin with, I should be somehow just by running an LP, Anyway, I'm finding a vertex of the polytope. Right?
No. But think of like which vertex. There might be a vertex which has some integral coordinates, but not all vertices have this property. And you want to find one such vertex. Just as in the discrepancy minimization problem, it was not even clear that there existed such a vertex. And in fact, these vertices are much fewer than the total number of vertices. They are exponentially small fraction of the total number of vertices, and you want to kind of isolate these vertices.
But they're closer to the origin. But on the other hand, they're somehow closer to the origin.
Yeah.
I know people to find them.
So maybe if you expand your definition of rounding, maybe you can include it. But my sense of rounding is you take a fractional, point and then get to the integral point, which.
So it gets to the integral point iteratively, and if it fails, let's say it gives the all zeros thing, which is like a trivial rounding. It doesn't give anything meaningful there. I think it's a rounding algorithm in principle, and the applications also use this as a rounding algorithm. There's a way of rounding, using it to round discrepancy constraints and so on. And in fact, Lovasz also used it in this context. He finds the LP solution for this bin packing problem and uses our algorithm to round the LP solution.
Do you know how exactly?
Not really, because it's just like 2 or 3 weeks old, and I haven't had time to look at it. Okay, so here's the first part of the talk, and let me now talk about the second half. And here I'll just state our result and mostly talk about some applications. So what are central limit theorems? And I'm sure most of us know what limit theorems are, but let me just quickly run through some examples to basically to set up some notation. So the central limit theorem says that if you have n independent identically distributed random variables, then the sum of the variables after appropriate normalization looks like the standard Gaussian distribution. And it is one of the most basic results in probability and has many applications. And pictorially, here I have the probability density function of one random variable, 2 random variables, and so on. And you can clearly see the shape of the bell curve emerging. And another example is large deviation bounds in probability, which say that specifically for independent bounded random variables, the sum of independent identically distributed random variables, the probability it deviates too much from the mean, is somehow comparable to what happens in the Gaussian case. And such bounds are crucial for the analysis of many randomized algorithms, and they again fall in the same kind of broad paradigm of limit theorems, because you're comparing the behavior of sum of independent things to that of the Gaussian distribution. And why should we care about limit theorems in algorithms or in computer science applications? Mainly because they give us a nice way to translate discrete problems to continuous problems, where we often have many more sophisticated tools like calculus or convex geometry and so on. And one nice example of this philosophy is the method of convex relaxations for combinatorial optimization problems. Okay. So there you look at relaxations which are now continuous problems, and then you can do some rounding or so on. So limit theorems have a lot of applications in computer science, to voting theory or social choice theory, to learning theory, complexity theory, communication complexity, and also in pseudo-randomness. And here I'll talk about one limit theorem and its applications to questions in voting theory and learning theory. So my work has led to 2 generalizations of the central limit theorem to multidimensional and discrete versions, which are motivated by such applications and problems in learning theory. And here I'll talk about the multidimensional version. So to motivate the multidimensional central limit theorem, let us look at a special case of the classical central limit theorem. It says that if you have n random plus or minus 1 signs, then their sum looks like the standard Gaussian distribution, which is a very, very special case of the central limit theorem. But there's a geometric way of looking at this result, which is as follows. let's say you have the the universe of the n-dimensional space denoted in 2 dimensions here due to limitations of PowerPoint. And red squares you should think of as n-bit Boolean vectors, and blue circles as Gaussian random vectors, random Gaussian vectors. And the central limit theorem says that if you take a hyperplane in n dimensions, which slices this space, then the fraction of Boolean points that lie on one side of the hyperplane is close to the fraction of Gaussian points that lie on the same side of the hyperplane. Okay? And given this geometric interpretation, it's natural to ask what happens if you have, instead of having one hyperplane, you have 2 hyperplanes. Is the fraction of Boolean points on the same side close to the fraction of blue points still? What if you have 3 hyperplanes? Or more generally, you have many hyperplanes which now form a polytope. And this leads to the question of central limit theorem for polytopes. So you have a polytope in n dimensions, and we'd like to know if the Boolean volume of the polytope, which is the probability that a random plus or minus 1 point lies inside the polytope, is close to the Gaussian volume, which is the probability that a random Gaussian vector lies inside the polytope. And this is what we'll show a limit theorem in this context, but let me just put some conditions under which our theorem will hold. So we'll assume that our polytope has a polynomial number of facets, because that's the most interesting case for applications. And most importantly, we'll also assume that the polytope is regular, in the sense that no variable is too influential for any of the bounding hyperplanes. Let me explain this. So geometrically, this says that the polytope, none of the bounding hyperplanes of the polytope are aligned with the coordinate axis vectors. For example, the hyperplane x1 will not be regular, and the hyperplane x1 plus, the sum of all the xi's is a regular hyperplane. And regular polytopes appear reasonably commonly in dense integer programs and so on. But most importantly, regularity is needed for such central limit theorems. Without regularity, you cannot have a central limit theorem, so it's a reasonable assumption to make. And in joint work with Harsha and Clivans, we showed that if you have such a regular polytope, then the Boolean volume of the polytope is close to the Gaussian volume with an error which is lit law of 1. The lit law of 1 is actually something like log squared the number of faces, but it's most importantly lit law of 1. So the error goes to 0 as the dimensions go to infinity.
Does the lit law of 1 depend on how far these planes are from the coordinate axes, I guess?
I mean, not in terms of the distance from the origin, but in terms of orientation.
Angle. Yeah,
in terms of
okay.
angle. Yeah, it does.
Okay.
Yeah, exactly. So here's our statement, limit theorem restated. And once again, the notable thing here is that it beats the union bound. There's a rich body of literature on multidimensional central limit theorems. But unfortunately, if you apply those results in our setting, you end up with a bound which is at least linear in the number of facets of the polytope. And at its heart, or implicitly, I think this is because when you specialize those theorems to our setting, you end up bounding the error for a single hyperplane and then kind of taking a union bound across the different hyperplanes.
So then why do you need the condition that it has polynomially many facets? Because
so
you're not taking a union bound.
Right, so wait, say that again?
So why do you need, why doesn't your result apply for?
So it applies to the most, the error is actually, it applies for any polytope with any number of facets, but it's the easiest to write down. So if the number of facets is k, the error is like log squared k. So as long as k is maybe slightly sub-exponential, you get something meaningful.
If you allowed exponential, you could shave off all the corners of
Yeah, but like, of course, not exponential, but there's a lot of stuff between polynomial and
Right. We can handle up to something like 2 to the root n or 2 to the n to the some power. And yeah.
But again, it doesn't depend on the distance of the faces from the object, so it
No.
somehow captures the large deviations case as well?
No, I think it's too. It's too imprecise for large deviation bounds because it's not capturing the behavior at the tails. Even in the usual central limit theorem, you can't get large deviation bounds from that. And our bounds are actually nearly optimal. We get comparable lower bounds as well. So we get something like log squared k, and the lower bound is square root of log k. And before going into the applications, I won't have time to delve too much into the proof, but let me say a few words. The first thing I want to say is what makes us think this is possible, that you can beat the union bound in this context. And if you look at the literature in probability, one of the main techniques they have for proving limit theorems are these variational methods. And at the core of them is if you want to bound the error, you need to bound the probability of some of regions which are close to the boundary. So when you do the analysis, things which are very close to the boundary on either side, if they have too much volume, then you will be in trouble. And for the case of polytopes, let's say you start with your polytope and look at all points which are at a distance of epsilon from the boundary of the polytope. So you get k of these strips like this, like the one shown here. And there's a beautiful result due to Nazarov, who showed that the Gaussian volume of these blue regions is actually square root of log k times epsilon. And if you use the union bound, you get a bound of k times epsilon, because each strip has a volume of epsilon, and there are k of these strips. So this is one of the places where you beat the union bound, and knowing this result was what prompted us to think such results exist, and you can use it.
So what is k?
K is the number of facets.
And this is in 2D.
This is in n dimensions, but the figure is in 2D. PowerPoint. Okay. And finally, the actual proof of the result uses this. This is one place where we beat the union bound. And we also use some other results from non-trivial results from convex geometry. But what I find surprising is the proof actually uses techniques that were developed in the context of designing pseudo-random generators. So the result has nothing to do with pseudo-randomness or designing PRGs. But somehow the proof was at least morally inspired by those techniques. You can de-randomize it, but without the pseudo-randomness part, we probably wouldn't have come across this, at least us. Okay. So let me now talk about the applications of the limit theorem, and we'll see how to use the limit theorem to beat union bound in various cases. The first application I want to talk about is to noise sensitivity. Let's say you have some election where people cast their votes, and you decide the outcome of the election based on a majority. And what we are interested in here is what if there are errors in registering the votes. So you have these votes again, and there are errors, and what we'd like to know is if the errors cause the outcome of the election to change. And this can be captured by this nice concept from the analysis of Boolean functions called noise sensitivity. So you have some Boolean function f and some noise parameter epsilon, and the noise sensitivity of f is the probability that the function evaluated at a random point changes its value when you perturb each coordinate of the random point with some probability epsilon. Okay. So coming back to the voting scenario, so the election scheme here will be decided by the function f, and noise sensitivity is the probability that if you flip each vote with some probability, with error probability epsilon, the outcome of the election changes. That is noise sensitivity.
And x is also at random.
X is also at random value. Yeah. So it has many applications in analysis of Boolean functions, starting with the work of Kahn, Kalai, and Lineal, who implicitly use it to show some Fourier concentration properties. Hastad in '97, who used it to show some optimal inapproximability results. Benjamin, Kalla, and Schramm, who formally, I think that's the first place it was formally defined. And also use it for some questions in percolation and so on. And here I want to talk about noise sensitivity of majorities, or more generally, weighted majorities. And here Perez showed that the noise sensitivity of any weighted majority with noise rate epsilon is at most 2 times square root of epsilon. Okay? And as we've been asking before, when you have a question about one majority, it's somehow natural to ask what happens if you have 2 majorities or 3 or 4 or several majorities. And this leads to the problem of computing or bounding the noise sensitivity of polytopes. So you have some polytope in n dimensions, and the noise sensitivity of the polytope geometrically means the following. So you generate a random point, and we're interested in the probability that when you perturb this point, it ends up crossing the boundary. Right? You take a random point, perturb it, and we want to know when will it, how likely is it to cross the boundary of the polytope. And using our limit theorem, we can show that the noise sensitivity of any regular polytope is at most poly-logarithmic in k times a factor which is polynomial in the noise rate epsilon.
So these are again Boolean points.
Yeah, Boolean points, yeah. And once again, this beats the union bound, and the best previous result was basically said that you have a bound on the noise sensitivity of the single hyperplane, and if you have k things, the noise sensitivity can increase at most by a factor of k.
Sorry, k is the number of spaces.
K is the number of facets. Yeah. And how does the proof go? At a high level, the proof basically says the following. So you want to compute the Boolean noise sensitivity. We use our limit theorem to translate the Boolean problem to the Gaussian world, where the Gaussian analog of noise sensitivity is the surface area or the Gaussian surface area of a polytope. And there's a beautiful result of Nazarov, which I briefly mentioned before, says that Gaussian surface area of a polytope with k facets is square root of log k times epsilon, the square root of log k. So here it's important that our limit theorem itself have very good dependence on the number of facets. Because if you lose too much in the limit theorem, even if you have very good bounds for the Gaussian world, you don't get anything. So we had to beat the union bound in both cases. And one application of our noise sensitivity bound is to learning intersections of half spaces. And let me skip this application for now. And let me just summarize by saying that in both of these cases, we bet the union bound by using some geometric techniques, especially some symmetric properties of the Gaussian distribution. And there's another example of along the same lines in my work on computing the supremum of Gaussian processes. Let me briefly mention some of my other interests, and then I'll conclude. So one of my major focuses has been in pseudo-randomness and constructing pseudo-random generators. And there been focusing on constructing pseudo-random generators for geometric shapes like half spaces, polynomial threshold functions, polytopes. And here the pseudo-random generators are naturally motivated by questions in complexity theory, but they also have applications in algorithms, especially to dimension reduction, counting solutions to integer programs, and so on. And to bounded space algorithms, where they're helpful for making some streaming algorithms efficient and simulating random walks efficiently, and so on, to bounded depth circuits and to counting algorithms. So that is one thread. And another thread is hardness of approximation, where the focus of my work has been on the unique games conjecture, which is probably the most important open question in this area, and which, if true, would solve many other important open problems, like the complexity of max cut, vertex cover, sparsest cut, and so on. And here my work gives the best evidence in support of the conjecture and suggests a qualitative approach for proving the conjecture by using alphabet reduction. And this is one of the things I thought about in the past and will probably think about in the future. And in learning theory, my work has focused on learning half spaces, polynomials, and more recently to adapting the smooth complexity framework from algorithms to make certain seemingly intractable problems in learning theory tractable. And I also done work in data mining, where the focus has been mainly on matrix rank minimization problems. So you have a bunch of linear constraints on matrices, and you want to find the minimal rank matrix which satisfies these constraints. And this has many applications, matrix completion, such as a Netflix challenge or recommendation systems, computing metric embeddings, kernel learning, and so on. And here, this is more empirical work, so the focus has been on giving simple and practical algorithms which scale well for high-dimensional data and also have some nice rigorous guarantees. So in summary, my work has basically been around using the structure of randomness in the form of limit theorems and the geometry of randomness for various questions in algorithmic proofs or complexity theory, pseudo-randomness, learning theory, and vice versa. And it is these connections, I think, that form the core of my research, and I'd like to explore these things in the future. Thank you.
Further questions? Many of us have further time for questions from the later.
I have one. Do you have what's the best lower bound on noise sensitivity of polytopes?
Of polytopes, you need square root log k times epsilon. Square root of epsilon. Up to some constants. If you have a polytope with k facets, it seems like the
Epsilon.
right, epsilon to the half and square root of log k.
We have a log squared.
We have log squared and also the regularity assumption.
So you have
Root log k.
Right.
so is it possible to push this?
So I think it might be easier to push the k down than to push the epsilon down, because I think getting square root of epsilon in our techniques might be much harder than like we use what's called the Lindeberg method, and even for a single, like if you use that method even for the central limit theorem, you end up getting a bound like epsilon to the 1/5. So that might be more harder than the k.
So for small k, there's nothing better than this k root epsilon.
Right. So yeah, our result it beats the union bound, but it has the regularity assumption.
It beats the union bound only if k is large.
Right. Yeah. That.
Right. Thank you again.